Start talking about set theory today. And before we start talking about solving any problems or anything like that, we have to do some definitions. Okay? So firstly, let's talk about what set theory is. Set theory is basically studying collections of objects and studying relationships between collections of different objects. So actually we've seen this before when you guys actually looked back in grade 10 at the collection of the real numbers, and we divided them into different sets. For example, the rational numbers and the irrational numbers. And then within the rational numbers, we had smaller sets, like the integers, or the whole numbers, or the natural numbers. And those were all sets of numbers. And the numbers were these objects that were within each set. Okay? So a set itself is basically a collection of objects. Okay. Now, to show that we are talking about a set, we have to use curly brackets. To denote a set. Okay, so something like this. And in fact, we've seen that before when we've looked at domain and range. And that's because the domain and the range of a function is a set of values, right? It's a set of values that is defined for that particular function. Okay, so let's say, for example, we're talking about the set of primary colors. And I'm going to define set P to equal the set of red, blue, and yellow. Okay, that's an example of a set. The objects that are within the set do not necessarily need to be numbers. They can also be colors, they can be people, they can be other things as well. Okay, each object is called an element. So an element is an object within a set. Okay, so for an example, red is an object within set P. Okay. Now there are three different ways that we can list a set or list the elements of a set. Okay, so let's say, for example, we're talking about, let's say we're using the set of faces on a six-sided die. Okay. Well, one thing that we can do is we can just list all of the different elements that we might see. So if you think about what you might see when you roll a six-sided die, well, we could see the numbers 1, 2, 3, 4, 5, or 6. Okay? So that is one way of defining a set, is just by listing all of the values in the set within the set of curly brackets. Another way is that you could describe the set within the set of curly brackets. So we could say we're talking about natural numbers that are less than 7. Okay. Or you can also use set builder notation. Now, set builder notation is something that you would have seen before in domain and range. It's not something that's required for domain and range in this course. With set notation, or sorry, with set theory rather, you would be required to recognize what this means, but you wouldn't necessarily be required to come up with it yourself. So using set builder notation, if we were to define this set, we would say the set of n such that n is less than 7 and n is an element of the natural numbers. And we'll talk in a minute about what natural numbers are if you have forgotten what those are. Okay, now this over here, n of a, okay, that's called the order of a set or the number of elements within the set. Okay, so for this set above, okay, if we called this set set A, the number of elements in A is 6, because there are 6 different numbers that you could get on a 6-sided die. Okay, now back to this business of natural numbers and things like that. One thing that is important in this unit is that you do know the difference between things like integers, natural numbers, whole numbers, because that vocabulary does come up quite a bit, and it's expected that you know the difference. Okay, so I just want to review that very quickly. Okay, so whole numbers, actually let's maybe start with integers. Okay. Integers are like positive and negative whole numbers, so no fractions or decimals, but like -3, -2, -1, 0, 1, 2, 3, and then it keeps going in either direction, right? So like -1.2 is not an integer because it has a decimal part, but negative numbers can be integers, those are fine. Whole numbers, those start at 0. 0, 1, 2, 3, and they keep going. And then the natural numbers, they're also sometimes called the counting numbers. Those start at 1. And they keep going. Okay, and so that's why I use the term natural numbers to describe the numbers on the faces of a die, because 0 is not one of the faces of a die. Okay, so let's just do a quick example here. Let's consider 2 sets. One of them is set P and one of them is set R. So P are, the elements in P are whole numbers less than or equal to 5, and R are whole numbers less than 9. Okay, so let's start by listing the elements of P. Okay, so firstly, whole numbers. Whole numbers start at 0. So those include 0. And less than or equal to 5. That means we can include 5. So 0, 1, 2, 3, 4, and 5. And then R, odd whole numbers, less than 9. So less than means don't include 9. We don't include that value of 9, and it starts with odd numbers. So we're not going to include 0. It's just going to be 1, 3, 5, and 7. Okay, so we've listed the elements in each set. What is the number of elements in set R? That's what this notation means. The number of elements in that set is 1, 2, 3, 4. Okay. I'm going to skip this one. I'm going to let you guys look at this one yourselves, and you can also look at this in the completed notes. It's similar to the one that we did above, and the key is that you really have to interpret the description, right? Natural numbers less than 10, factors of 10. Okay, actually, you know what? Never mind. We're going to do this one because one thing that's really important is that you also don't confuse factors and multiples. So let's actually do this one as well, because that's something that can sometimes get confused. Okay, so natural numbers less than 10, that's set A. So natural numbers start at 1. Less than 10 means we don't include it. So 1, 2, 3, 4, 5, 6, all the way up to 9, 7, 8, and 9. Factors of 10. factors are things that 10 can be divided by. Okay, so another two words that come up in this unit sometimes are factors and multiples. Okay, and multiples are like copies of 10. So 10, 20, 30, 40, 50, 60. Factors are things that 10 can be divided by, like 2 and 5. 10 can be divided by 2 and 5, that kind of thing. Okay, so B would be, well, 1 and 10 always work, and then 2 and 5. 1, 2, 5, and 10. Okay, and then what is the number of elements in A? The number of elements in A is 9. Okay, all right, more terminology. Okay, the first thing that I want to talk about when we're considering well, actually, before we do that is let's just use these few sets to help us describe some terminology. So we're going to talk about U, and U is whole numbers less than 10. So let's just list those quickly. Whole numbers less than 10. Whole numbers start at 0. So 0, and then we go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. E is even single-digit whole numbers. Okay, so let's take this apart. Even means can't be odd, so 2, 4, 6, 8. 0 is also even. Single digit means it can't be double digits. Okay, so it can only have one digit, and it's a whole number. So it's one of these numbers that we've just listed above. Okay, so even, so 0, 2, 4, 6, 8. We can't use 10 though, because that's not single digits, that's double digits. Okay, so that's set E. L are whole numbers less than 6. Okay, so those would be the whole numbers up to 5. 0, 1, 2, 3, 4, and 5. And then O we're going to call the whole odd numbers less than 7. Okay, so whole odd numbers less than 7. So odd numbers less than 7 start at 1, and then 3 and 5. Okay, so these are all of the little sets that we're going to look at when we define some vocabulary below. Okay, so the first word that I want to talk about, or phrase I suppose, is called the universal set. And the universal set is the set that contains all elements under consideration for a particular problem. Okay, so set containing all elements under consideration for a problem. Okay. A subset is a smaller set that contains some elements within the universal set that are also in the universal set. Okay. A smaller set that contains some of the elements from the universal set. Okay, so on a global scale, we may be talking about the universal set being all students at Central Memorial High School. And a subset of that larger set are the students in this class in Math 30-2. That would be a subset of the universal set of students at Central Memorial High School. Okay. Within the problem that we have above, though, okay, U is the universal set because all of the other sets contain elements that are also within U. So U is the set that contains all elements that are under consideration, and then all of the other ones are subsets of U. Okay, they are smaller sets that have some of the elements of U, but not all of them. okay? Now, to show that something is a subset of another set, we use this symbol over here. It's kind of like an elongated C, and that is the notation that we use to show that one set is a subset of another set, okay? So in this example above, the set E, right, even single-digit whole numbers, is a subset of the universal set because 0, 2, 4, 6, and 8 are all within U. This one is in U, 2 is within U, 4 is within U, 6 is within U, and 8 is within U. So we can say E is a subset of U. Okay? Another example is we could say students in math 30-2 are a subset of students at Central Memorial High School. Okay? Now, if something's not a subset, then we just use the same symbol with a slash through it, like that. Okay? So is E a subset of O? Well, if we go back and look at E and O, is E a subset of O? No, it's not, okay? Because the elements in E are not in O, right? So in order for something to be a subset, all of the elements in E must also be in O, and that's not true. So what we would write is that E is not a subset of O. Okay? Is O a subset of L? Yes, it is, right? Because if you look at O and L, well, 1 is in L, 3 is in L, and 5 is also in L. So yes, O is a subset of, oh, sorry, not E, that's L, right? Oh, no, that says L. Sorry, it's hard to see on my smartboard. That does say L. Yes, O is a subset of L. Okay? Now, above here, I kind of skipped over this, but we've got something over here called a Venn diagram. And you guys have probably seen these before, either in math class or perhaps in other classes as well. And these diagrams sort of visually show the relationships within these sets as well. I'm going to go into more detail about these Venn diagrams in a few minutes. Okay? Now, an empty set. An empty set is a set that has no elements. Okay? Okay, and we use the following symbols to denote the empty set. One of them is this one. It's like a 0 with a slash through it. Or you can use a set of curly brackets that are kind of right next to each other, which means that nothing's in there, right? It's a set with no elements. So both of those symbols mean the same thing. It means that there are no elements in that set. Okay? Now, example of an empty set. In this particular example, we have to list just anything that wouldn't be in the universal set. So for example, I could say, let's say I defined a new set. T is multiples of 10. Okay. Well, if U is my universal set in this example, then set T is empty because multiples of 10 start at 10, 10, 20, 30, 40, 50, 60, etc. None of those are in the universal set because the universal set only goes up to 9. Okay? So, right, this only goes up to 9. So if we're using the same example and U is the universal set, which are all of the elements under consideration, then set T would be empty because there are no multiples of 10 in this universal set. Okay, so that's just one example of an empty set, right? We could say T is empty. And you could define many others. You could also say that another set Q is 11, 12, 13. That would be another example of an empty set. Okay? All right, more vocabulary. Okay, so the next thing that I'd like to talk about is something called the complement. Okay, so the complement of a set is anything that's in the universal set, but that's not in the set. Okay, so complement of set E is denoted by E complement. So we use this like apostrophe to denote a complement. Okay, now we have to go back and just think about what was in set E. So I got to go back a page and just see what that was. Okay, so E was 0, 2, 4, 6, 8. Okay, so I'm just going to write this up here because I don't have it handy, but U is 0, 1, 2, 3, 4. We're using the same example. 7, 8, 9. And E were the even ones, right? 0, 2, 4, 6, 8. Okay, so E complement is anything that's in the universal set that's not an E. It's almost like the opposite of E. Okay, so as I'm going through U, I'm like, okay, 0 is an E, so it's not in the complement. 1 isn't though, so I'm going to put 1 in there. 2 is an E, so that doesn't work, but 3 isn't. So it's all the ones that aren't, right? 5, 7, and 9. Okay, and then list the elements in L complement. Well, L, I can't remember what L was. L was whole numbers less than 6. Okay, so if L is whole numbers less than 6, that was everything up to 5. Whoops, 2, 3, 4, 5. Okay, well then L complement is going to be everything else. So if you think of L being from 0 to 5, then L complement is the rest of it from 6 to 9. Okay, so that is what the complement is. Now, one thing that's also important to know about a subset and its complement is that if you add them together, you should get the universal set, right? So if I take a look at E, which is 0, 2, 4, 6, 8, and I add E complement, 1, 3, 5, 7, 9, if I add all of those elements together, I should always get the universal set. Okay, because the definition of the complement is everything that's not an E that's in the universal. So when you add them together, you always end up with the universal. Okay, and the same goes for L and L complement. So you may want to make a note of that. Okay, E plus E complement equals U. Same with L. Okay, and that's generally true. Disjoint sets. Okay, disjoint sets are two subsets that have no elements in common. Okay, that share no elements. So I believe we have to go back to, I have to go back to the previous page because I can't remember what these were, but like O and E, right? E was even numbers, O was odd numbers. Those ones would be disjoint because they share no common elements. Okay, so for example, O, which is 1, 3, 5, and E, which is 0, 2, 4, 6, and 8. Those are disjoint. All right. Now, back to this Venn diagram. Okay. A Venn diagram is basically a graphic organizer or a visual organizer that shows relationships between different groups of sets and subsets. And when you have a universal set with two subsets, then there are three different situations that can go on. Okay. Now, firstly, and I've got a picture of all three of them below. So before we get into that, one thing that I want to just tell you quickly is that in all three of these diagrams, the universal set is represented by the rectangle. Okay, so these rectangles over here represent the universal set. Okay, so those are all the universal sets. And then when you have two subsets within a universal subset, you can have one of three things happen. One, the two subsets are disjoint, meaning that they have no common elements. Okay, so that would be situation A. Okay, no common elements. Okay. The second thing that can happen is that the subsets could share some elements, but not all. So they could have partial overlap, and that's the middle one. Okay, so here, the subsets share some common elements. And then the third situation that's going on is basically one subset is a subset of the other one. Okay, meaning that in this inner circle, all of the elements that's on the inner circle are also in the other subset. Okay, so the inside subset is a subset itself of the outside one. Okay, now when we are actually drawing a subset to show relationships between sets, we have to decide which scenario we're in. Okay, so the first thing that we're going to do is we're going to draw a rectangle for the universal set. Okay, and then the second thing that we need to do is we need to draw two circles for the subsets. And we have to decide which of the three scenarios we're in. So we actually have to compare subsets and say, are we in a situation where they have no elements in common, in which case we draw the one on the far left? Are we in a situation where they have some common elements but not all, which is where we draw the one in the middle? Or is one subset entirely contained within the other? Okay, so draw two circles for the two subsets. And you have to decide which of the three situations above applies, I suppose. Okay? Right? So if elements belong to more than one, subset, okay, then the circles will either partially or completely overlap. which means we're in one of the two right situations. Okay? And then the final thing that you need to know is that if there's an element that's in the universal set, but that's not in one of the subsets, we have to draw it outside the circles, but inside the rectangle. In U, but not in a subset, or I should say place it outside the circles, but in the rectangle. And when we do an example, this will become pretty clear. All right, so let's try one. Okay, draw a Venn diagram representing the relationship between multiples of 2, 4, and 20 up to and including 16. Okay, so part A, list your sets as elements where the universal set is all natural numbers less than 17. So this is always a good thing to do, right? When you're doing a problem, list all elements in your universal set and list all elements in your subsets. Okay, so our universal set is natural numbers less than 17, so that's 1 to 16. Okay, there's the universal set. And then we're looking at relationships between multiples of 2, 4, and 20, up to and including 16. So let's call set A multiples of 2. So multiples of 2 are 2, 4, 6, 8, 10, 12, 14, 16. Okay, multiples of 4, we'll call that set B. That would be 4, 8, 12, and 16. Within the universal set, we have to stop there because the universal set only goes up to 16. And then multiples of 20. Now, within this universal set, there are no multiples of 20. So this is empty. Okay. Now, if we're going to draw a Venn diagram to represent this situation, well, the big rectangle represents our universal set. And then we have these two smaller sets, A and B. Okay? So what we need to decide is, firstly, is there any overlap between A and B? And we can see there is, right? There are elements that are common to both. And in fact, when we compare more closely, all of the elements that are in B are also in A. So we're going to have a scenario where we have this subset A, and B is entirely inside of A. Okay? Now what we're going to do next is we are going to put all of the elements that are in B first, right? We're going to start with the very inside. So that's 4, 8, 12, and 16. Okay? Now one thing that's also important is that every element can only go into the rectangle once. So once I've put 4 in B, it's already in A, because B is inside of A. So I'm not going to put that in again. What I have to put on the outside, right, on this sort of blob on the outside, that's outside of B but inside of A, are all of the numbers that are inside A but not inside B, like 2, 4 I've already got down, 6, 8 I've already got down, 10, 12 I've got down, 14, and 16 I've already got down. Okay? And then everything else that's in the universal set that I haven't already put down on my page yet has to go on the outside. And this happens to be all of the odd numbers. So I'm going to put 1, 3, 5, 7, 9, 11, 13, and 15. Okay? And those all go on the outside. Okay? Now C. C is an interesting one. Okay? Empty sets happen to be subsets of everything because nothing is inside of everything. So C is right in here. We could put C right in the middle, and it's empty. There we go. Looks like a 0, but maybe I should put it in a different color. Oh well. All right, so which sets are subsets? Well, we've got a couple of subsets going on here. Okay, firstly, A and B are both subsets of the universal set, so we'll start with that. A is a subset of U. B is also a subset of U. Okay, and then B is also a subset of A because B is entirely in A. Okay, what is the complement of the set of multiples of 4? So that would, we defined that as B. So B complement is anything that's in the universal set that's not in B. So what you can actually do is you can put your hand over set B. And I'm doing this on the smartboard. You guys won't be able to see this. But if you put your hand over that little bubble and just list all of the other elements, then you will, that are in the rectangle, you will have the complement. So I've got 2, 4, 6, 14. And to be honest, you don't have to, but I tend to do them in numerical order if I can. So I'm going to go 1, 2, 3. Okay, and then I'm going to go 4 is skipped because that's in B. 5, 6, 7. 8 wouldn't go in because it's in B. 9, 10, 11. 12 isn't going to go in. 13, 14, and 15. And that's B complement. Okay? And then what set represents the empty set? Well, we talked about that. That is the set of multiples of 20. And that's because there are no multiples of 20 in U. All right. Okay, so I am going to get you guys to do this one yourself. This is one that I want you to try once this lesson is done. This is on page 8. The completed notes, though, are on D2L, so you guys can look at those if you are getting confused. And I will also address any questions once you guys are finished watching this lesson, if you have any. So I'm going to skip that one. And I want to take a look at this one. Do I? Yeah, let's take a look at a couple of these quickly. And then we'll call it a day. Okay, so here's one question. Oh, actually, wait, sorry. There's one piece of vocabulary that I skipped over. It's at the top of page 9. And that is mutually exclusive events. Okay, so mutually exclusive events are two events that cannot occur at the same time. Okay, so an example of two events that cannot occur at the same time would be Canada Day and Christmas. One of them is on July 1st, the other one is on December 25th. Those are mutually exclusive. Okay, so here's an example. Canada Day and Christmas are mutually exclusive. Okay. Another mutually exclusive event would be rolling a die and landing on an even and an odd number. Okay, that's mutually exclusive. Those can't happen at the same time. You either land on an even number or you land on an odd number. Okay? You can, on the other hand, land on an even number and a multiple of 3, because 6 is both even and a multiple of 3. So that's just to contrast something that maybe wouldn't be mutually exclusive, right? Or, for example, Christmas and a day in December are not mutually exclusive, right? Those two events can occur at the same time. Or Christmas and a Wednesday are not mutually exclusive because Christmas could happen on a Wednesday. Okay, so that's another piece of vocabulary that we need to discuss. And then we are going to do some examples. Now, one thing about mutually exclusive events is that on a Venn diagram, those two events would look like they're disjoint, right? There's not going to be any overlap if two events are mutually exclusive. Okay, Ina drew the Venn diagram below. What elements are in the complement of F? So here what we have here is this C is our universal set, and then we've got F, oranges, pineapple, bananas, and then a smaller subset in F is S, apples and pears. And then we've got another disjoint set, V, which is peas, potatoes, beans, carrots, and corn. So I'm going to guess that F is fruit and V is vegetable. What elements are in the complement of F? So F complement is everything that's not in F. That would be everything that's in V. So in this case, F complement actually equals V, which is peas, potatoes. I'm being lazy and just listing beans. I'm using the first letter, carrots, and corn. Okay, how many elements are in S complement? Okay, so anything that's not in S. Well, there's only 2 elements in S, which are apples and pears. So anything that's not in S would be in S complement. And the number of elements, that would be oranges, pineapples, bananas, that's 3, and then the 5 that are in V. So the number of elements, the way that we would write that, the number of elements in S complement equals 8. Okay. Are there any disjoint sets? If yes, let's list them. Yes. F and V are disjoint. Okay. Is S complement equal to V? Okay. Well, S complement is not equal to V because S complement also includes oranges, pineapples, and bananas, and those are not in V. No. Also includes oranges, pineapple, and banana, which are not in V. And then finally, list all the subsets. Okay, well, firstly, whenever you're listing subsets, don't forget that all of the smaller bubbles are universal, are subsets of the universal, right? And the universal set here is called C. So V is a subset of C. F is a subset of C. S is a subset of C. And then also S is a subset of F. Okay, and actually my thought is trying to figure out what S means. I think it's the fruit that you can eat the skins, because oranges, pineapples, and bananas you have to peel. Apples and pears you have to eat the skins. But that's up for interpretation. Okay, I'm going to let you guys look at number 2, and I'm Also going to let you guys look at numbers 3, 4, and 5. So I'd like you guys to look at those. I'd also like you to complete this homework over here. All right.